Hello, everyone. Welcome to Physics 205. In this lecture, we're going to talk about graphical interpretation. So basically what we're going to do is we're going to interpret position versus time graphs, velocity versus time graphs. We'll answer questions about each of those types of graphs. And then given a position versus time graph, we'll draw the corresponding velocity versus time graph, what that would look like. And given a velocity versus time graph, we'll draw the corresponding acceleration versus time graph. Okay, so you can think of these graphs as representing one-dimensional motion. The way I like to think about that is you have some object that's moving along the x-axis, and it could be doing one of three things. It could be moving in the positive x direction, to call that like forward. It could be moving in the backward or the negative x direction, backwards, or it could be at rest, right? So it's just one-dimensional motion. All these graphs represent one-dimensional motion. Okay, so what I'd like to do is I'm going to get on the iPad and I'm going to walk through many examples so you get an idea of how to interpret these graphs. Okay, so here we have a position versus time graph. One of the things you can see is that it's linear. We'll talk about what that means later. And the first question is, what is the average velocity over the entire 6 seconds that this object is moving? So remember, the definition of average velocity is, so I'll write it as Vx_av. It's going to be the final position in the x direction minus the initial position divided by the final time minus the initial time. Or we could write that as delta x, right? Change in position, which is displacement, divided by change in time. So if I choose that point right there, which has coordinates 0, 1, right? The time is 0 seconds and the position is 1 meter. And then I choose this point right here where the time is 6 and the position is 4. So if you want, you can think of this as, this is like t initial, x initial, and then this would be t final, x final. Or sometimes you use 1 and 2, t1, x1, t2, x2. Okay, so then if I plug these in, this is going to be x final, which is 4, minus x initial, which is 1, divided by t final, which is 6, minus t initial, which is 0. And if you work this out, this is going to be 3/6, which is 1/2. And of course, it has units. It's a velocity of meters per second. So the average velocity over that entire 6-second time interval is 1/2 meter per second. Okay. What about the second question? What is the instantaneous velocity at 4 seconds? Well, how do I figure out that? Well, if I go to the graph, go to 4 seconds, go up to the graph, and what I want to find there at 4 seconds on the graph is the slope. Notice how when we did this average velocity over the entire 6 seconds, what we really found was the slope of this line, right? The slope of the line connecting those two endpoints. Now, since the graph itself is linear, it happens to be the slope of the actual graph itself. Well, if I want to know the instantaneous velocity right at 4 seconds, I just want to know the slope of the tangent line, the line that just touches the graph right at 4 seconds. But again, because the entire graph is linear, that slope of the tangent line, so the slope of this line right here, that just touches the graph at 4 seconds, that's going to be the same as the slope of the entire line. So it turns out that the instantaneous velocity at 4 seconds is also going to be 1/2 meters per second. Okay, so actually both of these answers are the same, right? Because it's linear. So 1/2 meters per second, and the instantaneous velocity at 4 seconds is also 1/2 meters per second. And same thing any other time, right? If I said, what is the instantaneous velocity at 1.5 seconds? I go to 1.5, I find the tangent line, and I find the slope of that tangent line. Well, that slope is the same, right? So that, again, would be 1/2 meters per second. Okay, and notice anywhere on this line, at any time, we have exactly the same slope. Okay, so what does this tell us? Well, it says if the position versus time graph is linear, right, it's a line, then that means the velocity of the object is constant. Okay, so that's this last question here. If the position versus time graph is a line, what does that indicate regarding the velocity of the object? The velocity of the object is constant. Right, so that's important. If you have a position versus time graph that's linear, it represents constant velocity motion. Okay, let's try something a little bit different. Let's say now that we have a position versus time graph again, but now it's curved, right? In fact, in this case, it's like a parabola, so it's a quadratic function. And the first question we want to answer is, what is the average velocity over the first 6 seconds? Well, the average velocity only depends on the initial and final position, right? Again, remember that the definition of average velocity is it's the final position minus the initial over the final time minus the initial time. It's delta x over delta t. So again, I only have to look at those 2 points. So I look at the initial point right here, which is 0, 0. And then what do I want over for 6 seconds? So at 6, it has coordinates of 6, 2. So this is like 0, 0. And then 6, 2. So I'll call this, let me use ones and twos now. So T1, X1, T2, X2. So again, another way of calculating this, it's going to be X2 minus X1. So X2 is kind of like X final. X1 is X initial over T2 minus T1. So if you work this out, it'll be 2 minus 0 over 6 minus 0, which is 2, 6, which is 1/3. And again, it has units of meters per second. So what did we find when we calculated the average velocity? We basically found the slope of the secant line that connects those 2 points. If I draw a line there, that slope of that green line, that is going to be the average velocity over the first 6 seconds. Okay, what about the second? So that's the first question. What is the average velocity of the first 6 seconds? It's 1/3 meters per second. What about the second question? What direction is the object moving at 4 seconds? Well, the velocity of the object tells you the direction, right? If the velocity is positive, it's moving to the right or moving forward. If the velocity is negative, it's moving to the left, it's moving backwards. If the velocity is 0, then it's at rest. So how do I find the velocity at 4 seconds? I go to the graph. So I go to 4 seconds, go to the graph, and remember the velocity is the slope of this tangent line here that just touches the graph at that one point. Well, in this case, that slope is positive. We don't know the value. We could probably estimate it if we wanted to, but we don't know that value. But we know it's positive. So that means that the object is moving forward, right? In the positive x direction, which we're going to call forward. So I'll just write moving forward. Okay, as time passes, what is happening to the velocity of the object in this case? Well, again, if we start at the beginning, right, at 0, it's pretty much, the slope of the tangent line is pretty much also going to be 0, right? It's pretty much flat there. So that means the velocity, which is the slope of that tangent line, is 0. Then now that slope increases a little bit, then increases some more. And you can see here the slope just keeps increasing. So that means the velocity, which represents that slope, is increasing over time. As time goes on, this object is getting faster and faster and faster, right? The velocity is increasing over time. So velocity is, I'll write like an arrow like that, increasing over time. Okay, now remember the definition of acceleration. Acceleration is the change in velocity over change in time. So any time that the velocity is changing in any way, it could be magnitude, could be direction. In this case, it's just the magnitude. It's getting greater and greater and greater. So since that velocity is changing over time, that means this object is accelerating. So the next question, the next answer would be yes. The object is accelerating. And the reason is because velocity is changing over time. Okay, what's a quick way of determining that if you have a position versus time graph? Well, if the position versus time graph is curved at all, that means those slopes, those velocities are changing, so it must be accelerating, right? So anytime a position versus time graph is curved somehow, that means the object is accelerating. Okay, next question. Now we have a velocity versus time graph, right? So instead of position, we have velocity. So for this type of graph, if I ask you a question about velocity, you can just read it directly from the graph. You don't need to calculate slopes anymore, right? Remember with the position versus time graph, if I asked you about velocity, you had to figure out the slope. But for velocity versus time graph, if I ask you a question about velocity, you can just read it directly from the graph. If I ask you a question about acceleration, that's going to be the slope of the velocity versus time graph. Okay, and then we'll talk about one more thing, displacement. Actually, we'll talk about it in the next example. If I ask you about displacement, like the change in position, it turns out that's going to be the area underneath the velocity versus time graph. Okay, so if I ask you about velocity, read it off directly. Acceleration, we have to look at the slope of the velocity versus time graph. And if I ask about displacement, it's the area underneath the velocity versus time graph. So in this case, the first thing I want to figure out is what is the velocity of the object at 4 seconds? So because I have a velocity versus time graph, I can just read that answer directly. So I go to 4 seconds, I go up to the graph, I read it off here, and it looks like it's 3 meters per second. So this is going to be 3 meters per second. I just read it directly from the graph, right? I went to 4 seconds, went up to the graph, and read off the value. Okay, over time, what is happening with the velocity of the object? Well, again, we're asking about velocity. We can just read it directly from the graph. What is the graph showing us? Well, as time goes on, right, what's happening with the velocity? It's increasing. And it looks like it's increasing at a constant rate. So we could say velocity is increasing at a constant rate. Okay, what is the average acceleration over the entire 8 seconds? Well, remember the definition for average acceleration. It's going to be the final velocity minus the initial velocity divided by the final time minus the initial time. Or you could write it as change in velocity. You can call that in the x direction, divided by change in time. Okay, so basically we want to find the slope, right? So if I pick a point here, this is going to be 0, 2, right? Those coordinates. If I pick the point here, because I want to do over the entire 8 seconds, this is 8, 4. I'm just going to call this T1, V1, and I'm going to call this point T2, V2. Instead of using initial and final, I'm just using 1 and 2. So what I want to calculate here is I want to calculate V2 minus V1 over T2 minus T1. So this is going to be 4 minus 2 over 8 minus 0. In this case, it looks like it's 2/8, which is equal to 1/4 if I simplify. And it has units of meters per second, which we always write as meters per second squared. So it looks like the average acceleration over that entire time period is 1/4 meters per second squared. So 0.25, right? Meters per second squared. Okay, what is the acceleration at 3 seconds? Right at 3 seconds. Well, to answer that question, I go to 3 seconds, that time, I go to the graph, and because I have a velocity versus time graph and I want to find the acceleration, I want the slope. And what do I want? what do I want the slope of? The slope of the tangent line that just touches the graph at 3 seconds. So basically be the slope of this line right here. Just touches the graph at 3 seconds, right? That, like that. But notice again, in this case, this velocity versus time graph is linear, right? So those slopes do not change. That's going to be the same slope as what I just calculated, right? They don't change over time. So in this case, the acceleration right at 3 seconds is also going to be 1/4 meters per second. Okay, now, again, because this graph is linear, regardless of what time I choose, if I calculate the slope of the tangent line at any of these times, I'm going to get exactly the same value. So that means the acceleration must be the same over all those time intervals. So if you have a velocity versus time graph that's linear, that represents constant accelerated motion. Right? So that's what this last question is saying. Because the velocity versus time graph is a line, what does that indicate regarding the acceleration of the object? The acceleration is constant. Now notice velocity is not constant, right? Velocity is increasing, as we can see from the graph, because it's velocity versus time. It's increasing over time, but it's increasing at a constant rate. It's the acceleration that's constant in this case. And actually, a lot of the problems that we deal with in this class, physics and movement science class, are going to be constant accelerated problems, constant accelerated motion. So this will be very, very common. Okay, next page. This is just an example of another velocity versus time graph. But in this case, if you look at the slopes of these tangent lines at some different times here, see how those slopes are changing? In fact, they're increasing over time. So what does that, remember, each of those slopes represents the instantaneous acceleration at that time interval. What does that say about acceleration? It's saying that it's changing, right? It's increasing over time in this case. Okay, this would be an example if and we'll learn this later, if the net force acting on the object is increasing over time. That means the acceleration of the object would be also increasing over time. This is less common of the type of examples we're going to be dealing with in this class, but that could be a possibility where the acceleration itself is changing. Okay, and then this example, so again, this is a velocity versus time graph. But now I want to ask the question, what does the area underneath this graph represent? So if you, let me see if I can just sketch this out here. So this is the 0, right? This is the x-axis. What does this area, if I calculate this entire area here, what does that area represent? It turns out that area represents the displacement of the object. Okay, so the area underneath the velocity versus time graph represents the displacement of the object. Okay, so the area underneath represents the displacement. Okay, how do we know that? Well, I can give you a sort of a quick idea of why that's the case. Remember the definition of average velocity in the x direction is going to be delta x over delta t. If I solve that equation for delta x, which is the displacement, I'm going to get it's the velocity times the time. Okay, and notice here, if you look at this area underneath the graph, actually, let's just look at this point, this part right here where it's just the velocity is constant. So this is just a rectangle here. Notice that This is simply the time, right? This is like 2 seconds. This is the velocity, which is also 2 meters per second. If I multiply them, right, think of like length times width, then I'm going to get an area, but that area in this case, so velocity times time, which is like length times width, represents the displacement. So the area underneath the velocity versus time graph is going to be the displacement. So this, what I want to answer in the second part is, what is the object displacement over the entire 6 seconds? Well, the way to figure this out is, let me break this up into 2 objects that I know. I basically have a triangle here. Okay, so this first part is just a triangle. I'm going to call that A1, area 1. And then I have this rectangle, which we just talked about a little bit. So the rectangle, I'll call that A2. And then if I can figure out, if I can compute A1 and then compute A2, right, by using known geometric formulas, then I can add them together, and that must be the area underneath the entire velocity versus time graph, which is going to be the displacement. Okay, so, well, what is A1? Well, remember the area of the triangle is 1/2 base times height. So I have 1/2. The base is going to be what? I guess it'll be from here to here, so 4. So base is 4. And then the height is going to be 2. So that looks like it's going to be 4 meters. And then for A2, this is just a rectangle, right? So length times width, or you could say base times height, same thing. In this case, it looks like the length is 2, right? Which is really seconds, 2 seconds. And the width is going to be 2 meters per second. So this is 2 times 2, which is also 4 meters. And if I add those two together, so that's going to be 4 plus 4, I'm going to get 8 meters. So, but that is, when I add them together, that is my displacement. So the delta x, the change in position, the displacement, is simply the area underneath a velocity versus time graph. So in this case, it's going to be 8 meters. Now, in this example, notice that the velocity was always non-negative, right? It started at 0, it was positive, and then it stayed positive at a constant value here. So the area, the displacement, was just positive. It turns out at the velocity, and I'll do an example like this in a little bit, if the velocity is negative, then you have to find the area underneath the x-axis up to the velocity graph. Okay, so you end up like subtracting, because basically you're saying you're going backwards. In this case, we're going forward, so the displacement is positive. But if you're going backwards, then that area is going to be underneath the x-axis or the time axis, and that's going to contribute a negative displacement. Okay, I'll do an example like that in a few minutes, and it'll make more sense. Okay, so knowing that, let's do some practice here. Let's say I have this position versus time graph. Okay, and we want to answer all these questions. And then ultimately, if you look at question F, we want to sketch the corresponding velocity versus time graph based on this position versus time graph. Okay, so first, let's start with these questions. What is the object's velocity at 1 second? Well, it's a position versus time graph. Remember, to answer a question about velocity, I have to calculate the slope. And if I want the velocity right at 1 second, then that means I want the slope of the tangent line that just touches the graph at 1 second. So I want the slope of that line right there, right, that blue line. But notice here that the velocity is constant over the entire first 2 seconds, right? It's this slope right here. So if I can find, it's easier to calculate this slope, right? If I can find this slope, then I know the answer to my question, because I have this slope right here, which is the slope of the tangent line right at 1 second. So that would be the instantaneous velocity at 1 second. Okay, so basically what I'm saying is the velocity is constant over the first 2 seconds. So if I can calculate the slope of this line, then I have my answer. Well, we could pick this point here, right? 0, 1. We could pick this point here, 2, 3, and then just calculate it based on x final minus x initial over t final minus t initial. But even easier, right? And this is just quicker. Remember, another way of writing the slope is we could say it's rise over run. That is the same as saying delta x over delta t. So in this case, if I start here and I want to get to here, my rise, I have to go up 2, right? Because I'm going from 1 to 3. So I'm going up plus 2. And then the run is I'm going over plus 2 seconds. So this is simply going to be 2 over 2, which is 1. And it has units of meters per second. So we know that the slope of this line is 1 meter per second. And the slope of the line that just touches at 1 second is also 1 meter per second. So that answers our question. What is the object's velocity at 1 second? It's exactly 1 meter per second. Okay, where's the object at rest? Well, it's going to be at rest where the velocity is 0, right? And how do we know the velocity is 0 if we have a position versus time graph? That means the slope must be 0. So wherever the velocity is 0, wherever the position versus time graph is flat, right, where its slope is 0, that must be where the object's at rest. So it looks like from 2 to 4 seconds, it's at rest, and 5 to 6 seconds. So from 2 to 4 seconds and 5 to 6 seconds. Okay, when does the object have the greatest speed? Well, remember when we ask about speed, speed is the magnitude of velocity. Velocity is a vector, right? Even one-dimensionally, it has a sign, either positive or negative. Speed is not. Speed is always positive. It's just a scalar. It's just the magnitude of velocity. So if I'm asking where does the object have the greatest speed, I'm looking for the location where I have the steepest slope, right? It doesn't matter if it's positive or negative. So here it looks like the slope is 1, right? We already calculated that one. Here it looks like the slope is -3, right? Because it's going down 3 over 1, so -3. And here it looks like it's going up 1 over 2, so it looks like it's 1/2. So -3 is the velocity here, but that means the speed is going to be +3, right? It's the absolute value. It's going to be 3 meters per second. Here the speed is 1. Here the speed is 3. Here the speed is 1/2. So it looks like between 4 and 5 seconds, I have the greatest speed. Okay. The velocity happens to be negative, but the speed is just the absolute value. This is the magnitude of velocity. So I'll say between 4 and 5 seconds. 4 and 5 seconds. Does the object ever move backwards? Well, what tells us the direction of the object? It's the velocity. Here, we know the velocity is positive, right? Because it's +1. Here, we know it's at rest, 0. Here, it looks like it's negative. Here, it's 0. Here, it's positive. So we're just looking for where we have a negative slope, right? Where the velocity is negative. So it looks like between 4 and 5 seconds again. That's when it's moving backwards. 4 to 5 seconds. Okay, when does the object have the greatest positive velocity? All right, so now I'm looking for the greatest positive slope. Well, again, here it's 1, here's -3, so that's not going to affect it. And then here it's 1/2. So it looks like between 0 and 2 seconds, right, where it's +1 is going to be the greatest positive velocity. So between 0 and 2 seconds. Okay, and now I want to sketch the corresponding velocity versus time graph. So again, between 0 and 2, what is the velocity? Well, it's 1 meter per second, right? We already calculated that. So let me go to the velocity graph. In between 0 and 2, I know the velocity is, so between 0 and 2, the velocity is 1 meter per second. And it's constant, right? That slope doesn't change here. So that means it's constant velocity. Now, here's one thing that's a little bit, and this is just for teaching purposes. See how this graph, this velocity jumps from 1 down to 0? and there's no like, there's kind of a kink here. There's no like smooth. The reason why I do that, it's just easier to, for teaching purposes, teaching it this way. So in reality, this would have to like kind of smooth down to 0 and then be smooth here. But for teaching purposes, it's much easier just to have it jump, okay? So from 2 to 4 seconds, the velocity is 0, and it literally jumps to 0. So if I go down to this graph now, from 2 to 4, it's going to jump to 0. So let me draw it here. 2 to 4, it's going to be 0. You don't even connect them. It literally goes from 1 and then jumps down to 0. Now, that's not physically possible, but again, for teaching purposes, that's what the graph does in this case. Okay, what about from 4 to 5? Well, from 4 to 5, let me calculate the slope because I want the velocity. The rise is -3, the run is 1, so it looks like the velocity is -3, right? That slope is -3. So if I go to my graph here, from 4 to 5, the velocity is going to be -3, like that. Okay, 5 to 6, 0 again, right? So 5 to 6, it's 0. So like that. And then finally, from 6 to 8, it looks like, let's see, the rise is 1, right? To go from here to here, I want to go up 1 and then over 2. So it looks like +1/2. So it looks like it's going to be +1/2 or 0.5, right? So something like that. So that would be my corresponding velocity versus time graph. This velocity versus time graph corresponds to that position versus time graph. Okay, next example. Now I'm giving a velocity versus time graph. So again, if I ask a question about velocity, you can read it directly from this graph. If I ask a question about acceleration, now we have to calculate slopes, right? Because the acceleration is the change in velocity over change in time, which is a slope. And if I ask a question about displacement, that's going to be the area underneath the velocity versus time graph. Okay, so given all that, let's see if we can answer these questions. So in this case, the first question is, does the object ever move backwards? Well, remember, what tells us the direction of the object? It's going to be the velocity. So the velocity would have to be negative for the object to be moving backwards. Now you have to be careful here, right? If this were position versus time, right? If this is position and this is time, then you're looking at slopes. But this is velocity versus time, this graph. So I can just look at the graph directly. Are these velocities ever negative? Well, no, it's like 3, then it goes down to 1. It's still positive, right? Back to 2, down to 0. Right here, it's like 0, but it never becomes negative, never goes in this area. So in this case, this object is always moving either forward or it's at rest the last second here, from 7 to 8 seconds. So it's never moving backwards in this case, right? Because the velocity is never negative. So does the object ever move backwards? No, not in this case. Is the object ever at rest? Yeah, we just said where the velocity is 0, so between 7 and 8 seconds, it's at rest. Is the acceleration ever negative? Okay, well, the acceleration is going to be the slope, right? The slope of this graph. So is the acceleration ever negative? Yep, the acceleration is going to be negative from 0 to 1 second, right? That slope is negative, which is the acceleration. And then also from 5 to 7 seconds. So 0 to 1, I'll just write that way. And then 5 to 7 seconds. Is the acceleration ever 0? Well, for the acceleration to be 0, it means the velocity versus time graph would have to be just horizontal, right? Flat, where the slope is 0. So is the slope ever 0? Yeah, right here, right? Between 1 and 3 seconds, and also right here, right? Between 7 and 8 seconds. So here we have the object is undergoing constant velocity motion. It's just staying at 1, so there's no acceleration. Again, we can see that there's no acceleration because it has no slope, right? 0. Here, the velocity is constant. In fact, it happens to be 0, right? The object's at rest, so there's also no acceleration between 7 and 8 seconds. So is the acceleration ever 0? Yes, between 1 and 3 seconds and 7 and 8 seconds. When does the greatest positive acceleration occur? Well, the greatest positive acceleration is going to be where we have the largest positive slope, right? Because remember, the slope of velocity versus time graph represents acceleration. So here we can eliminate that. That's negative, right? Negative acceleration. Here's 0. Here's positive, negative, 0. Oh, so actually in this case, the only one that's positive is here. So that must be the greatest positive, right? So between 3 and 5 seconds, we have the greatest positive acceleration. In fact, it's the only part of the graph where the acceleration is positive. So between 3 and 5 seconds. Okay, what is the velocity at 4 seconds? Well, I'm asking about velocity. I can read the value from the graph directly. So I go to 4 seconds, I go up to the graph, and I read off this value. What is it? 1.5, right? Meters per second. So the velocity at 4 seconds is 1.5 meters per second. What is the acceleration at 6 seconds? Well, to figure that out, I go to the graph, I go to 6 seconds. I want to calculate the slope, but in this case, I want the slope of the tangent line, right at 6 seconds. But over this interval from 5 to 7 seconds, from 5 to 7, it turns out it's linear, right? The slope happens to be constant. So over this entire interval, we have the same slope, the same acceleration. So if I want to find this slope of this tangent line, it's easier just to find this slope of the entire line, right? Because it's the same. Acceleration happens to be constant over the entire time interval. So what is that slope? Well, if I start here, to get to this point, I need to move down 2 and then over 2. Okay, so -2, that's my rise, and my run is a +2. So -2 divided by +2 is going to be -1. So -1 meters per second squared. Okay, and then finally, let's take this graph and sketch the corresponding acceleration versus time graph. Well, to do that, I need to, right, I want to find the corresponding acceleration versus time graph. I need to find all these slopes now, right? So I want to plot basically all these slopes. So from 0 to 1 second, I need to find the acceleration, which is constant, and it's going to be this slope right here, right? Well, what is the slope? My rise looks like it's -2, right? Because I'm going from 3 to 1, and my run is a +1. So -2 over 1 is -2. So from 0 to 1, my acceleration is -2. So something like this. Let's see, 0 to 1, it's -2. So like that. Then let's see, from 1 to 3, what is this acceleration? Well, the slope is 0, so the acceleration is 0 from 1 to 3. So from 1 to 3, it's 0. From 3 to 4, actually, no, in this case, I'm going to go 3 to 5. So from 3 to 5, it looks like the acceleration is constant. And let's see, the rise is a 1 and a run is 2, right? So, and it's positive, so +1 over 2, right? The rise is 1, the run is 2. So it looks like it's 1/2 from 3 to 5. So let's see, 1/2 would be like this. From 5 to 7. So 5 to 7, it's going to be this slope, which we already calculated, which is what it was. Rise was -2 over +2, so -1, right? The acceleration is -1 from 5 to 7. So -1, 5 to 7. And then finally from 7 to 8, what is this slope? Well, it's 0 again, right? So the acceleration is 0 from 7 to 8. That's 0. So that will be the corresponding acceleration versus time graph. Okay, last example here. So now we have a velocity versus time graph, and we're asked several things about this graph. So first of all, I want to know what is the velocity of the object at 0.5 seconds, at 3.5 seconds, and at 5 seconds. Because I have a velocity versus time graph, I can read these values off directly, right? So if I want to know at 0.5 seconds, I go to 0.5, I go up to the graph, I read off that value. It looks like it's 2.5 meters per second. So this is going to be, I'll do it like this. I'll say velocity at 0.5 seconds is equal to 2.5 meters per second. Okay, what about the velocity at 3.5 seconds? Well, I go to 3.5, right here. I go to the graph. I read off that value. It looks like it's -2, right? So -2. So velocity at 3.5 is -2 meters per second. And then finally, I want to know the velocity at 5 seconds. So I go to 5, go to the graph, read off the value. It looks like it's -3. So this is going to be -3 meters per second. Okay, what is the acceleration at those 3 times now? So same 3 times, I want to know the acceleration. So I want to know I'll call it A, acceleration at 0.5. I want to know the acceleration at 3.5. And I want to know the acceleration at 5. Well, now that I want to know the acceleration, I need to find the slope, right? I need to find the slope of the tangent lines at all of those instants in time. So I need to find the slope at 0.5, which is the slope of this tangent line right here. But that's the same as the slope of that line, right? Because the acceleration happens to be constant from 0 to 1 seconds. So what is that value going to be? Well, if I do rise over run, so I'm starting at 4, I'm going down to 1. So I'm going down 3, and it looks like over, you got to be careful here with the way I did units. It looks like over 1, right? So down 3 over 1. So it's going to be -3 over 1, which is -3. So the acceleration at 0.5 seconds is -3 meters per second squared. Now, what about the acceleration at 3.5? So I go to 3.5, I go to the graph, I want to find the slope of the tangent line that just touches the graph at 3.5, but that's the same as the slope of this entire line, right? Because the acceleration happens to be constant over that interval. So now let me just do rise over run. So I'm going from 1 down to -3, right? So that looks like I'm going down 4, so -4, and then over 2, right? Because I'm going from 2 to 4. So down 4 over 2, -4 divided by +2 is -2. So that's going to be -2 meters per second squared. And then at 5 seconds, I want to find the acceleration. So that's the slope of that line. Well, that's easy, right? That's going to be 0. So that'll be 0. The velocity happens to be constant over that interval from 4 to 6 seconds. There's no acceleration. So 0 meters per second squared. Okay, when is the velocity of the object negative? Well, again, we're asking a question about velocity. We have a velocity versus time graph. So I'm going to just look at it and figure out when the velocity is negative. Well, it looks like it's negative from this point, right, which is what, 2.5 seconds. It's negative, it's still negative up until 7 seconds, right? So it looks like from 2.5 to 7 seconds, it's negative. So from 2.5 to 7 seconds, that's when it's negative. Is the object at rest? Well, sort of. It has a velocity of 0 at 2 instants in time. So you can kind of say it's at rest just for an instant in time. When does that occur? Right at 2.5 seconds, right here where the velocity is 0. and right at 7 seconds, where the velocity is 0. So let's say at 2.5 seconds and at 7 seconds. Okay, what is the displacement of the object over the entire 8 seconds? All right, so now to figure out displacement, I need to calculate the area underneath this velocity versus time graph. Because these are, just lines, I can make nice, easy figures, just of triangles and rectangles. This, by the way, would be more complicated if you had a more complicated function. You might have to use calculus, or there's other ways of estimating it. But for us right now, we could just estimate it by calculating the area of known geometric figures, basically triangles and rectangles. So to do this, right, let me start here. I'm going to split this up, say right here, I'll call this A1, this little triangle here. Then this piece I'll call A2 up to here. So I have a little rectangle there. Maybe this little triangle right here I'll call A3. Now, here's another little triangle, right? A4. But remember, A4 is going to be a negative displacement, right? I have to take into account because the velocity is negative now, so that's going to be negative. Then I'll make a little rectangle here. This will be A5, another little triangle, A6, and a little triangle, A7. Okay, so let me calculate each of these, and then we'll just add them all up. All right, so A1. It's a triangle, right? So it's 1/2 base times height. It looks like the base is what, 1 in this case, and the height is 3. So 1 and then 3. So this is going to be like 3/2. Okay, A2. A2 is what I'm calling this little rectangle here, right? So that's length times width. So it looks like the length is what, 2, and the height or the width is 1. So it'll be length times width, so 2 times 1, which is 2. A3. A3 is this really tiny little triangle here. It looks like, so it's 1/2 base times height, right? So the base looks like it's 0.5, and the height looks like it's 1. So 1/2 base times height, so 1/2 times 0.5, which is also 1/2, right, times 1. Looks like that's like a quarter only. Okay, A4. A4 looks like the base is what? It's going from 2.5 to 4. So it's 1.5, and the height is 3, but it's negative. So it's 1/2 times 1.5 times 3. So that's going to be like, I think it's like 9/4, right? 1/2 is, or 1.5 is the same as 3/2. So it looks like it's going to be 9/4, but it's negative, right? Because it's underneath. The velocity is negative, so that means the displacement is going to be negative. So negative 9/4. A5 is just this rectangle here. So the base is 2, the height is 3, so it's like 6, but also negative. Many times width, so 2 times 3, which is 6, but it's going to be negative. A6 is 1/2 base times height. So it looks like 1/2 times the base. It's going from 6 to 7, so that's 1, and the height is 3. Again, it's negative, so it's negative 3/2. And then finally, A7 will be positive again, right? Because it's above, the velocity is positive now. So 1/2 base is 1 times height is 1. So it's going to be 1/2 times 1 times 1, but positive. So that's going to be 1/2. Okay, so now if I add all of those areas up, that's got to be my displacement, right? So my delta x is going to be a1 plus a2 plus a3 plus a4 plus a5 plus a6 plus a7. So if you do this, right, you're going to get 3/2 plus 2 plus 1/4 plus -9/4 plus -6 plus -3/2 plus 1/2. Okay, if you do all this, if you add this up, you're going to get -22/4, which is -5.5 meters. So that's my displacement. So it turns out, like wherever you started, you're going to end up 5.5 meters back from where you started. So if you started at like x equals 0, your final position is going to be -5.5 meters. And the reason is, if you look at this, you're traveling with negative velocity more than you're traveling positive velocity. So that's why the total ended up being like a negative 5.5. Because there's a greater area that's negative here than there is that's positive. Okay, so your change in position, your displacement is negative 5.5 meters in this case. All right, now one last thing. Given this velocity versus time graph, let's sketch the corresponding acceleration versus time graph. So again, to do that, I just need to calculate the slopes, right? And just plot the slopes on this acceleration graph. So I go back here. So from 0 to 1 second, what is this slope? Well, it's -3 over 1, right? So -3. So 0 to 1, it's going to be -3 like that. Okay, from, let's see, 1 to 2, that's easy. The slope is 0, right? So the acceleration is 0 from 1 to 2. So 1 to 2, it's 0. From 2 to 4, so from 2 to 4, it looks like it's constant, right? So we can calculate the slope. So I'm going from 1 to -3, right? So that's the rise is a -4 and the run is a +2. So it looks like it's going to be -2. So from 2 to 4, it's -2. Something like that. Okay, from 4 to 6, it's easy. The acceleration is 0. So 4 to 6, acceleration is 0. From 6 to 7, let's see, do rise or run. So it's going, the rise is going, it's going from -3 to 0. So it's going up 3, right? And then over 1. So +3, right? From 6 to 7. So 6 to 7, my acceleration is a +3, like that. And then finally from 7 to 8, let's see, it's going up 1 over 1. So it looks like my slope is a +1 there. So from 7 to 8 seconds, I have an acceleration of +1. Okay, so that would be my acceleration versus time graph that corresponds to that velocity versus time graph. All right, so it does take practice to get this, but then it'll all start clicking, it'll all start making sense. We also will be doing a lab on this as well. So there'll be one of the labs will be just on graphical interpretation. Great, thanks.